usual, get started on this. Right, let's see if we share the screen and it works. Can you see my screen properly?
Yes, now I can.
Okay, cool. All right, folks, welcome. We're getting there. This is sort of our last week of instruction, and then next week, on Monday, we will do a review and we'll be ready for the exam. One important announcement about that is we'll be doing the exam through HonorLock. And Nathan, if you could get them onboarded this week, then we'll be all set. If you need any help about the setup, etc., then let me know and we can talk. We do this regularly for our online class because it's all remote. We normally, of course, don't do this for our regular on-campus classes, but hopefully this will be the only semester which we had to do it. It works very easily. You get a time slot assigned to your exam as per the Oscar, and we'll enable the exam exactly at that time. In Canvas, you log in and you answer the questions, and then you put in the answers in the text boxes which are provided as a part of the HonorLock exam itself. Unfortunately, it doesn't allow you to draw pictures and many other limitations are there. So we will, of course, ask you to bring your own blank paper, work out all these solutions there, and then the intermediate answers and the final answers and some explanation is what you can put in a text format, which will give. Of course, we are not going to auto-grade it. It's just that we will be using HonorLock as a way of administering it. So it will, of course, the exam will be on April 30th at the time that is given by Oscar. Some of you had asked me a question whether I will change the exam. I don't like the way it is currently. It is too late in the day. Unfortunately, the GT rules don't allow me to do any changes because it might conflict with somebody else's exam schedule and so on, and we may not be able to find a common time, and that's the reason why GT strictly prohibits any instructor, not just me, from changing the time at all. It's really not out of my hands, so unfortunately we had to live with that. Hopefully you can grab a little early dinner and then do it, and we'll be finishing it, of course, in the early days of our exams rather than the later days, so which is a good news, so that you can be free then. So Nathan, look into that one, the onboarding, so that everybody is set up on their laptops and so on. And we will ask you to bring blank sheets of paper to work out the solutions. We'll talk a little bit about the exam in next week when we do the review. So it's comprehensive. We never had any exam in this class. So just to give you a heads up, all topics are there, and the duration and all, you know it, about 5-6 questions will be there roughly. So and it will try to cover all the different topics. I'll talk more next week. So let's get back to our work. The topics that we were in, and we'll finish this fairly quickly and do a review of register allocation, and then the next lecture will be devoted to seeing a machine-dependent optimization, which is based on a paper which leverages register allocation. So that's what is coming up. Hope all of you are making good progress on your remaining part of the project, part 2, as well as the homework 4, which should be fairly easy to do on paper and pencil, but that's due on this Friday, the homework. And of course, the project is due next week, Monday, part 2. So we were looking at the last 2 optimizations. We looked at loop fusion, which is an important optimization, which allows you to improve the locality of a loop. For example, if you have A being generated in the top loop and being used in the bottom loop, and for not this size of an array, but a very large loop, and which has lots of references, you might send A out of the cache if you have these loops executing like these. However, if you merge them into one loop, then you will be able to gain advantage of the locality. And in doing so, you must preserve the dependencies in the merge loop. So what we do here is, first and foremost, we must make sure that both the loops execute the same number of iterations. So what you have here is the top loop going from 1 to 99 and the second one going from 1 to 98. So that won't work. So we peel an iteration here. This is where the loop peeling becomes very useful. Typically the first iteration, now the first loop goes from 2 to 99, which is total 98 iterations. Bottom loop is similar. Sometimes this is not a compile time known like a number, but it's in terms of n, but typically you also have n and n minus 1, something like that, in terms of the same symbolic constant n, and that also allows you to do this peeling. And once you have aligned this way, then you normalize it going from 0 onwards, and then you try to fuse the loops. So here you can see that that's exactly what we have done. We have a normalized loop 0 to 97, and then from that we have derived from that induction variable IB, we have derived the loop, the array indices for A of I and I plus 1, and those are given by the respective IB plus 2, IB plus 1, and that has generated the correct references here. So as though the loop is executing 2 onwards and the bottom loop is executing 1 onwards for the respective number of iterations, and writing into the correct array locations for A, for the right values of B's, and so on. And you can see that a given iteration here is doing the right thing in terms of writing the value into A of I and then I plus 1. And you can see that we have generated these 2 different indices as the correct values as per the different iterations. And this one was a forward dependence there in the original loop. You can see we had generated all the new values in the top loop, and then all those new values were sort of read in the bottom loop before fusion. And the same dependence we had to maintain when we do this particular fusion. So you can see that that is exactly what is going on. IB plus 2 is 1 iteration ahead of IB plus 1. And so we are writing a new value, and in the next iteration of IB, we are really consuming that value over there. So the dependence is maintained here. as far as the values of the flow dependence is concerned. We're generating a value in 2 iterations ahead of IB, and then in the next iteration of IB, we are actually consuming that value in AI plus 1. And so this will be maintained as a loop carried dependence, flow dependence, as far as A of I is concerned. Originally, it was a forward dependence across 2 loop nests. And now it will be maintained in this particular way. And so obviously there will be a locality which is present in this loop through this loop carried dependence, which is generated now for A. A2 will be generated, for example, and A1 will be used in a given iteration, and then in the next iteration A2 will that is generated will get used. So again, it's the loop carried flow dependence. So because of which, obviously, this loop which is generated exhibits locality but has lost parallelism. You can see that in the original loop nests, which were separate, which were not fused, we had parallelism. We could execute the first loop totally, all the iterations in parallel, and then the second one could go in parallel. Unfortunately, that is lost here because of the loop carry dependence. But that can be remedied by shifting the bottom loop one iteration further. In other words, the question is, can we generate the the bottom references in such a way that A of I is generated and is consumed in the same iterations. That is possible. So give it a thought. If we are able to shift the iteration space a little bit, you can see that instead of I going from 1 to 98, if we make it from 2 to 99 and regenerate these references, you will be able to see that you will generate A of I and A of I plus 1 will consume in the same iteration. So there is no other dependence here, fortunately, which precludes that shift. And by doing so, we will avoid a loop carried dependence and gain locality as well as do the parallelization. Going to the next example, this does the reverse. What we have here is a loop which is fused and or a very big loop, and this is kind of rare these days because in the earlier days of parallel computing, the local caches and all were smaller. To make the data fit, some of this fission was being done. Now even L1 cache is substantially big, 64 KB and so on, and usually you don't have such huge loops which need fission. So this is kind of rare, but just to illustrate the issue here, what we have done is taken this loop, analyzed its dependencies, and they are as follows. See that S3 and S4, we have a flow dependence with distance 0. That means it's within the loop iteration for B. And then from 4 back to 3, we have again a flow dependence, which is generated because of C. So value of C is generated in iteration 4 in a given statement 4 in a given iteration, and then that same value is consumed one iteration up away after one iteration in statement 3. So that's why it's a backward dependence from 4 to 3, which is also flow. And then there are other dependencies. You can see from S3 to S2, we have a dependence again because of B, which is a flow. And we have S4 to S5 again, C, flow dependence. But that's the first one is the loop carried, the second one is loop independent. So given this particular dependence graph, which has found these dependencies, and you have also these distances and so on here, how can you break this loop down? That's the question, into pieces if you need to. See here, if you examine this dependence graph, S3 and S4 sort of form a cycle here. And so you cannot break this into two pieces because although you might obey the flow dependence from S3 to S4, if you split the loop, you're going forward. The problem will be in terms of going backward from C to CI. In other words, if you break the loop between 3 and 4, we will end up using either the old value of BI or old value of C. So that is not possible depending on which one we execute before what. The CI value must be new value generated in statement 4. So in the current lexical ordering, if you break it, we will end up losing that dependence, which is flow dependence, and executing old value coming into CI from top, and that will be wrong semantics. On the other hand, if we put 4 before 3, we'll end up using old value of B and not the new one, and that's also a problem. So you cannot break in between S3 and S4. Now let's see if we can break between S3. The answer is yes. You can see that S2 generates a flow value, S3 rather, generates, which is going as a new value being consumed in 2. So if we take this S3, S4 loop nest and organize it as the first loop, keep them together, S3, S4, organize that first loop, and then after that execute the S2, that will be just fine because it will enforce the flow dependence between BI and BI minus 1. In a similar way, after the S3, S4 loop nest, if we do statement 5 as a separate loop, it will also enforce the dependence between CI and square root of CI from 4 to 5, and that will also be fine. So the loop nest that we can generate here by this could look like we first do the 3 and 4 together, and then we do the number 2 as I was mentioning, and then the number 5 and so on. And we could again do this normalization, although that is not really necessary here. It's just shown for the convenience. And we can therefore split it into smaller loops. And what is the advantage? If we split it into smaller loops, then if the bigger loop was not fitting in a cache, that problem would be gone now. Or the other possibility may be that the original loop was not parallelizable. This is a more interesting case because of the dependencies, etc., as a whole. But now you cut out the pieces which are sequential under the dependence constraint and separated the parallel part of the loop, and you could take that parallel part into a different loop nest after doing fission, and you could go ahead and parallelize that part and leave out the sequential part. So think of some example in which original loop across iterations you could not parallelize, but what you did was you isolated the part which had the sequential dependencies and the transitive closure like forward and backward dependence statements all being lumped together. And now you separated, just like in this case, 3 and 4 out, that part out, which happened to be sequential because of such dependencies and so on. And the other pieces are not really dependent. You can see here that even in this particular case, AI, the statement number 2 is fully parallelizable now, and so is statement number 5. But in the original loop, because of the dependencies that are a part of the loop body, the original loop was not parallelizable across the iterations, and whereas this one has been is now potentially parallelizable because of this. This is a nice example of separating the sequential loop 3, 4. Here's out the dependencies, convert the others into forward dependencies, which get satisfied, and then take a loop around number 2 and fully parallelize, execute it in parallel. Number 5 is also same thing, no dependencies. And that's how you have now a nice parallelization of at least part of the loop, which was not originally there. So this is a better reason now for modern systems than trying to get around the locality which is affected because of small caches. So in short, what we do is we find out the strongly connected component and separate it out. And then we take the dependent components and we make sure their dependencies are satisfied. And we put those next to the one which they depend on, and then parallelize. So this is how it looks. We did S3, S4, and then the other ones. Okay, so we already talked about loop fission, loop reversal. I think we talked about it also last time. So if particular loop does not have any dependencies, loop carried dependencies, we can reverse it. You can see in this example that we want to kind of merge these two loops or fuse them. One is going and down to 1, but the other one is going up. But if you examine the second loop, di is equal to 1 over ci plus 1. It has no dependencies. So no loop carried dependencies. In this case, of course, loop independent dependence is also absent. But if you have loop loop independent dependence, that is AI is equal to BI kind of setup, then also we are fine in terms of doing the reversal. So AI is equal to AI plus 1 kind of thing is also fine as long as it's loop independent. So what we do is we execute this reverse to align these, and then you can see we are fusing these. And after the fusion, of course, we had to ensure that the original dependencies get satisfied here, which happens to be the case. And so that's basically the loop reversal. And you can see that originally here we had this problem about not aligned iterations. So now the last transformation that we are really interested in is loop interchanging. And as I said, this is one of the most important ones. And loop interchanging can be done even on for multiple types of cases. One of them is just by bringing in the inner loop inside, you can reduce the total number of executions of branches, etc. So that's shown here. If the outer loop iterates many times, inner loop executes only a few times. Interchanges reduces the startup costs of inner loop. The second one, more important, is if the loop is spanning the data space in a column major way, whereas the space is organized in a row major way, which is sort of the Fortran convention and so on. Due to this misalignment, you will pay a lot of, almost all the accesses will result in misses, cache misses. However, if it is aligned along the data organization or layout, all those will get converted into nice locality accesses because they'll cache lines. So if you're spanning along the row major and the data is also organized along row major, then you'll find lots of cache misses. If you span it along um, column major and the data is organized along row major, then it will create lots of misses. So of course you can't change the data layout because it will be very expensive, and it is also not allowed as per Fortran conventions, especially for libraries and all. They assume certain layouts. So then you interchange this loop, and as I was mentioning last time, we have this case of less than greater than, which is a problematic case, and that leads to the interchange. For all others, the interchange is possible. Like if you take less than equal to, for example, then the dependence was being enforced by the outer loop, but now it will get enforced by the inner loop. And that's perfectly fine. As far as the iteration space is concerned, it's just a inner loop which is enforcing that. So less than equal to is fine, less than is fine, equal to, well, all these are fine. But this vector which is shown here, less than greater than, this is a problem. Why is it a problem? Because now the dependence in the original loop nest is really enforced. You can see in this example by the I loop, I and I minus 2. So what is really going on is, in a given outer loop iteration I, you are writing into A of ij, and then the inner loop executes for all j values, and then another iteration occurs in the outer loop, and in the two iterations downhill, the A value gets consumed, which is generated in the I loop. So that is why you can see that the ordering, the iteration space ordering, is such that this value is generated in the given I iteration, and then two iterations down from there, it is really getting consumed, and because of that, you have a flow dependence. If you interchange it, however, J loop becomes the outer loop and I becomes the inner loop. And you can immediately see here that the J iteration in which you are reading comes ahead of the write. So earlier write was ahead of the read, which was a flow dependence. But now, because the J plus 1 bears a higher value than J, the iteration which carries out the read for the J dimension occurs before I, because the other J, and because of that reason, you have changed the dependence from flow to an anti-dependence, and because of which you are really changing the semantics. So one may say that, okay, there is no inner loop, any other dependence, we might reverse the inner loop, and that will change the direction vector. If you reverse any loop, the direction vector reverses its direction because of the negative indices where it works. So we might change that and convert this into less than by reversing J loop. That solution will work in general. But if you have multiple dependencies, one of them is less than, and another one is less than greater than, that solution will fail, because what it will happen is less than greater than will convert into less than, and then the less than greater than, which is here, will convert into less than, and less than, which was originally there, will convert into less than greater than. So you're back to again this problem of having to deal with this less than greater than dependence, and that won't work in general. So a general solution is to, as I was mentioning last time, is to skew the inner loop so that this less than greater than dependence becomes less than. how do you skew it? The idea is to shift the iteration space by some factor of multiplying with I, and by changing it instead of um, um, 2 to m, we want to do this particular iteration space from 2 plus f of I to m plus f of I. So we're just by multiplying each of the I iterations by f and adding it. So then how do we, of course, generate code for the original reference? Well, that has to remain where it was. So if we have j is equal to 2 plus f times of I, we got to recover j dash there, which is equal to 2. And so j dash will be recovered by using current value of j minus f of I. Whatever shift we have in, we will regain the original index j dash and then use that in the A's and everywhere j was being used for the indexing purposes. You can see that aj dash is there, and then a of I minus 2 plus I minus 2 and j dash plus 1 is also there. And this bj, there is a typo there. This should be b of I j dash, not b of I j, because the new index variable inside is j dash, which is recovered using j minus f times I. Okay, so that will preserve the array semantics wherever we are doing writing. It will be as per the original loop. You can see that we shifted it and then shifted it back by subtract shift, and that will keep it in the original array space, and everything will be fine as far as semantics is concerned. Now, what is the effect on dependencies? That is what we had to really worried about this dependence vector less than greater than. Does the dependence vector become larger, become smaller, or it has no effect when we skewed it with the outer vector by f? That's what we have to see. So let's work out some math here, which is not that difficult. So what we have here is let there be original dependencies between the original spaces as I1 J1 and I2 J2. Okay, in the as far as A is concerned. So I1 is the write iteration. The one I1 J1 is the iteration during which the writes takes place in the A space, and I2 J2 is the one during which the reads takes place in the A2's on the right hand side RHS value of the R value of A. So then if you equate the respective dimensions, you can see that I1 will be equal to I2 minus 2, and J1 will be equal to J1 plus 1 if you equate the respective dimensions to satisfy the dependence equations. So now let us see how this pans out in the skewed space. So we had to substitute J1 by J minus f of I1. Okay, the original whatever is recovered here, as we saw earlier in terms of indexing. So J1 dash minus f I1, because that is where the J1 is generated. So that gives you that equation on how J1 looks. And J2 occurs at the same time when I2 occurs. J2 is equal to J2 dash now minus f of. Okay, I hope this is clear. Because what has happened here is I1, J1 is occurring together, and that's generating J1. So in short, J1 dash is equal to J1 plus f of I1, which is what I just rearranged. And J1 therefore becomes J1 dash minus f of I1. And similarly, J2 iteration is recovered by J2 dash, which is a skewed iteration f of I2. So if you substitute these two for respective values of I1 is equal to I2 minus 2, and if you put this the value which is given here by um, um, uh, um, the relationship between these I1 and I2 and J1 and J2, you can see that left hand side, which is I1, is given to you by I2 minus 2 and J1 dash minus f of I1, which is uh, giving J1 is equal to is equal to J2 dash minus f of I2. So you can see here that um, what I have done here is kept the first one as it is, and the I2 minus I1 is basically what is 2. That's what I have substituted in terms of the respective um, uh, coefficients of things. So I hope you're following this. J1 dash minus f of I1 is equal to I1. Okay, so all that I did was I1 is equal to, I substituted I1 by J1 dash minus um, the I took the second equation, which is J1 dash. I took these two equations, I1 equal to I2 minus 2 and J1 dash minus f of I1 is equal to J2 dash minus f of I2. And from these two, I derived J1 dash is equal to J2 dash minus f of I2 minus I1. Since I2 minus I1 was equal to 2, I substituted I2 minus I1 as equal to 2 in this case. And so you had J1 dash, which is equal to J2 dash minus f of 2, f times 2. So from this particular equation, since I1 is less than I2 and J1 dash is less than J2 because of the factor f times 2. So what it is really showing here is the relation between original J1 and J2 was this, that J1 was greater than J2, but J1 dash now, which is related to J2 dash, is less. So J1 dash is less than J2 dash because of the difference being f times 2. Okay, so this particular equation therefore has changed from a dependence which was greater to and now the direction vector is less than, and because of which now the loop is interchangeable. So again, why did it really intuitively, if you look at it, I mean, mathematics is of course the right way to look at it, but if you really see what has really happened here is intuitively, the iteration J1 dash got boosted or from its original J1 value by a smaller factor, um, which was because of I1 is less than I2. Okay, by a smaller factor, which is 2 times f than J2 dash, and because of which, uh, even though J1 was greater than J2, J1 dash is less than J2 dash, J2 dash, by the factor of f times 2. And so, because of this reason, um, we have converted this less than greater than vector to less than vector. And in general, if you really analyze J1 dash minus J2 dash and rearrange these expressions, they come out like this. J1 dash minus J2 dash is equal to J1 minus J2 plus f of I1 minus I2. So we want to make sure that this J1 dash minus J2 dash becomes less than 0. And if you equate the right-hand side inequality to zero, less than 0, you can see that in order for that to be less than 0, the maximum value of um, uh, the differences between j should be less than minus f and minimum value of the difference between I. And so, in short, this skewing factor, f, whatever we call it, should be such that the max value of j should be offset here by the min value of I when you skew it. Then only these equations will get reversed from greater than to less than. And so if we choose the skewing factor to be greater than the maximum dependence distance in the j dimension divided by the minimum dependence distance in I dimension, we are always guaranteed that this particular skewing is going to work. And that's what we pretty much do. So go through this math again, which is really important for what happens to J1 dash and J2 dash difference, which is obviously in the original loop nest, J1 was greater than J2, but J1 dash is now less than J2 dash by f times 2 in this particular case. 2 here was, of course, a constant dependence distance, and the original dependence distance in the j dimension, it was just 1. So it came out that the skewing factor is equal to 2 or more. It should be f in this particular case. But in general, if it's varying, you can see that we need to worry about this right formula here, which is maximum dimensions maximum distance in j dimension followed by minimum in the I dimension, and that gives us the minimum value of f, which should be greater than this ratio. So so here's where we'll end our loop transformations. You know that this is just a scratching of the surface of the topic, but general ideas are important. When do we do loop skewing? We do it when we have conflicting dependencies, when we cannot reverse the inner loop, because if we reverse it, one of the less than will immediately convert into less than greater than, and again we will be back to square one. So which is the case many times. So what we do is we simply shift the inner loop by a large factor using some multiple of the outer loop iterations. And since I1 is less than I2, which in the original loops, and we are multiplying the I iterations by this factor of f, the shift on the j side for J1 gets shifted to J1 dash by a smaller magnitude than the J2, which gets shifted by a large degree. And so the originally J1 is greater than J2. However, J1 dash becomes less than J2 dash. And because of this reason, convert the original vector less than greater than into less than less than. And in this process, of course, we have to make sure that the shift is greater than the ratio of maximum j distance that must be bridged due to the shift by the I distance. And the minimum of I distance is we should be able to span using this factor f the maximum of j distance. So that's why this intuitive formula is very easy to see why it is delta j max divided by delta I min. F should be greater than equal to that. And that's what we ensure while shifting the iterations. And that allows us to convert less than greater than to less than less than. If there was already a less than, it will become even better because the dependence distance in the j dimension will increase here from where it was, and it will not become obviously less than greater than ever. So anyway, so this is the conclusion of, so what did we see in this particular transformations? We have all the dependencies. Many times we just have dependence vectors, and in some other cases we just have dependencies. We don't even know whether it is less than or greater than, or even what kind of dependence it is, flow or whatever. And we just use that information to split up a loop into parallel, non-parallel versions. When we know the dependencies, like in this loop interchange cases, we can do some transformation and convert them and allow the interchange. Why all these transformations are good? Some of them decrease the total execution count of branches. Some others bring locality, like interchange. Fusion is very important because it also allows us to do locality. And then loop unswitching and other things allow us to reduce the operation count. So they're all dependence-based transformations. Some of them allow you to, like index plate set splitting, allow you to split a loop into different pieces and parallelize parts of it and things like that. Even fission allows you to take out maybe some parts which are sequential, execute them separately, and fulfill dependencies and execute the dependent parts in parallel. So those are the reasons for loop transformations, and they're again having impact from just reducing number of executions of operations to enhancing locality to enhancing parallelism and so on. It's a big topic. 6245 deals with some of these in terms of parallel computing issues, but the core of this is about finding the dependencies. So I'll stop here. Any questions? Otherwise, we'll shift our gears and cover some background for register allocation today, and then we'll see its application in a different setting in the Wednesday's lecture. So I'll stop and see if you have any questions on these topics of loop transformations or any of these.
There are no questions on chat.
Okay, so then I'm going to go and download just a minute. So as we get set up for this, could you raise your hand if you have, of course, dealt with register allocation formally in terms of liveness analysis and graph coloring in your previous class? Like we do it here in 40-40, but I'm not sure if those who have come from other backgrounds could let me know if you have dealt with this topic or not. If you have dealt with it, including your implementation in a compiler, then raise your hand. If you just not dealt with it, keep your hand down. So if you have dealt with it in theory or in implementation, then raise your hand. And I just want to get a feel of how many are sort of exposed to this topic, not at all exposed to this topic. Could you, Nathan, tell me if how many?
2 people out of the 6.
Okay, 2 have been exposed. So if any of you have just learned it on paper and pencil theory, then raise your hand. If you've not at all been exposed, then this is a new topic for you. So do it one more time.
Now there are no hands raised.
Okay, so I assume that 2 of you have been exposed and done it as a part of theory or implementation. So I guess then we had to kind of look at it a little carefully here. This will be slight repetition for you, but those who have done, but I guess it's kind of inevitable. So I'm going to cover it here. Can you see my slides?
Yes.
Okay. So very important topic of backend in terms of giving out the registers to the memory locations which need to be held in registers. So let us look at what exactly is sort of, I'm going to set up, by the way, these slides on our web page, but just sort of very quickly talking about it. Typically, it is like this, that you have values which you are going to operate on. And what you can do is you can keep all these values in the memory and bring them into the registers through loads, operate on them, and then store them in the back in the stack. Or the other alternative is you maintain these values in registers. You continue to hold them in, let's say, R1 and R2 throughout their usage and operate on them through their register counterparts, and therefore you avoid all these kind of load stores since access to the memory is slow and so on. So the goal is to keep as many values as you can in registers. We have 2 kinds of registers, typically integers and floating point. There are also some registers for longer values like double words and so on. Then there are stack pointers and so on. But mainly we are going to operate on the integer and floating point values, keeping them in registers. So first question is everything safe to be kept in registers? That is, if you take an IR statement and say, hey, I want to put this A always in this register, is it okay to do so? So what is going on here is this, that in the von Neumann semantics, which is a memory-oriented model of IR and so on, you may have pointers which might be operating on those values which are alias to them. And because of that reason, it won't be safe to keep them. So you have to make sure that at a point when you're creating a register image, there is no pointer pointing to that value in its memory image. Otherwise, your value in the register will be stale and it will be wrong. So in other words, A is not safe to be kept at a program point P if there is a possibility of some pointer modifying A in the memory, and if it does so, then your value of A in register will be a stale value, which is an unmodified value, and because of which you should not be keeping that value in register. So pointer analysis, where to discover the unaliased values, etc., is very, very important for languages like C. In other languages, we know which value is pointed to by the pointer, like Java, and register allocation is much easier there. So what exactly is register allocation? So what we are trying to determine here is which values are first of all safe to be kept in registers. And then which values should be kept in registers if they are safe, because they have a use coming up soon. So that is called a liveness analysis. The value is going to be used few instructions down, so we should keep it in register. So that is what the liveness analysis does. And then once we determine these sets of values which should be maintained in the register, whether we find a register for that or not is the next issue to be addressed, because we have only 32 or 64 registers of each kind, and we typically have hundreds or thousands of values which could be demanding those registers at a program point. So the third one is basically what we call as graph coloring or register allocation problem. Here is a simple example of what's going on. So we have the original IR code on the left side, and what we do here is determine a range between the definition of a value and its last use. So you can see here that these live ranges, what we call it, is between the definition of a value, S1, to the last use of the value. You can see that S1 times S2 is the last time this value was used. So in this range is when we want to give a register to this value. We are of course assuming here that all these values are unaliased. They have been proved to be safe to keep it in registers, and we have different ranges here for different values. So the second value starts at the definition point and goes to, again, it's the last use of S2. S3 is in a similar way. S4 you can start at some other place and goes till the end, and so on. So these live range analysis is what is going to be first done to determine the ranges of usage of a value, quote unquote. And the value is supposed to be dead after this range. And during this value, it is supposed to be live, and we will be giving it a register when it is live, so that it will be able to operate on it through the register. And outside of that range, it is dead, and so therefore we will not keep it in a register. So the live range analysis will determine these ranges. And next, what we'll do is we'll construct what is called an interference graph. What exactly is the interference graph? The interference graph will show us that if two values are going to demand the register at the same time during their live range. So you can see here that if you consider S1 and S2, they have an overlapping live range. So they are going to simultaneously demand a register. However, if you look at S1 and let's say S6, you can see that S1's live range is ended, S6 starts after that. So they are not simultaneously live. They are not simultaneously going to demand a register. So what's the implication? We don't put any edge between them. And what is the implication of an edge? The implication of an edge in the interference graph is that they cannot share a register because they both demand it at the same time. Whereas when there is no interference edge, they demand it at different times, and therefore we'll be able to reuse the registers, let's say S1's register for S6 and so on. So we construct this first, the live ranges, then we find out which are simultaneously live by taking their intersection. And then finally, we build this particular interference graph in this particular way. And then the next thing that we do is we do some coloring on this graph that is giving out these registers. so that we are able to color it using a given number of registers. So let's say the question that is asked is, how can we color this with, let's say, 3 registers? Um, 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 and we can see the answer to that here is yes. We are able to give green color to S1, and therefore we cannot give the green color to S4 because it's interfering with it through that edge. We cannot give it to S2 and we cannot give it to S3. So we give out a different color, let's say red color to S4. And now because S1 and S4 both interfere with S2, we cannot give either one of those colors to S2. So we must give a totally different color blue to that. And then similarly, we can see that for S3, however, we can give the red color because it doesn't interfere with S4. If it were to interfere with S4, then we had to choose yet another color, maybe a fourth color, but here we can do with 3 colors. And similarly for S6, we have a choice of all different colors because it's all really not interfering with anything. So we could give either one of green or red or blue. Here we just randomly gave it this thing. And similarly for S5, we could have given it either a blue or green. We could not have given it a red because of interference, so we gave it another one. So typically the question that is asked is, given this interference graph and maybe 32 or 64 colors, how can you maximize the coloring of this graph, give out maximum number of nodes, some kind of color out of these 64 or 32 colors? Because what happens if we cannot give it a register? Then we had to put that node in the memory and we had to generate all kinds of load stores for that particular purpose. And what is the problem with load stores? The problem with load stores is it is going to cost us to, in terms of latency, to go to memory, bring that value, and it will be slow. The program will affect it because of this latency and memory operations that we have to carry out through those load stores. So once we do this register allocation, of course, at the IR level, we give it to the backend to do the instruction selection, generate the code, and whichever locations don't get registers, we generate the load stores for them, bring those values, operate them in temporary registers which are not given out. These are called as persistent registers because these values are maintained. Let's say we give S1 blue, green, then at the definition point, we will hold this in R1, you can see it. And wherever S1 is referenced, we will use R1, which is corresponding to the green one. So that allows us to avoid all these load stores when we are able to find a register for it. Otherwise, we would have to bring it from the memory. So what is the overall register allocation flow? I will introduce this overall flow, which is listed here. So first of all, as I mentioned, we have a liveness analysis, which is going to determine the live ranges for each one of the values. That is, from its definition to the last use is defined as the live range. Then we are going to determine what is called as a web, and let me introduce that concept through whiteboard. And then we are going to take this web and determine the interference on this. Then we are going to find out the cost of really not giving a register, or in fact, the load stores that will result, because if we cannot put this in a register, how much it will cost us, and that is called as a spill cost. Then we'll do the coloring by using this interference graph to decide which of these webs get a register, and then assign the registers to those. Others are spilled. What is a spill? That means they are going to be operated on through the memory, and then we'll decorate the IR using the registers that are given, or we'll leave their memory assignment intact there, and we'll give this to the code generator. The code generator will do the load store generation there for those which don't have registers. For others, it will generate the code into registers and operate them out of registers. And the efficiency of this particular process is really dependent on how well we are able to carry out this graph coloring business and give as many registers as possible to the underlying IR, and the rest of them are spilled, of course, which basically means that we'll have to pay for their cost to operate out of this memory. So let me introduce the concept of webs here. What exactly is going on and why we should be combining live ranges in a control flow graph in terms of webs. And that's something which is really important. So let me shift to whiteboard here and explain the concept of the webs and also the concept of live ranges in that particular process. And then the graph coloring part of this we will take up in the next lecture. So, and then we'll also talk about the paper which uses these concepts. So, so it's, by the way, register allocation is mostly machine independent. Optimizations is considered machine independent. But since it also ties sometimes to the organization of registers and their peculiar properties, it gets into machine dependent parts also. So let us look at the concept of webs. So what we have here is a very simple control flow graph. And what has happened here is a particular value V is defined here as a definition. This is another definition of V, V2. And we have this control flow graph and we have this use of V. So you can see that as per our definition of live range in this particular case, let's say this is our last use. There is no further use from here. So whatever control path we take this way or that way, we have no use of V. So this is our last use. So the live range is defined from a definition point to the last use. And let's say there are in between some uses of V here and here and V here and V here and so on. Okay, all these are in between uses. V gets defined here in V1, which is one of the definitions of V. Another definition is V2. And then the program flows here and V gets used. This definition that is used in these uses is V1. The definition that is used on this side is V2. So this is V1 here, this is V2, and so on. Now the question is, this live range that we have defined is this one, and this live range is also this one, from last use to the definition point. So now the question is, these two live ranges, should we treat them separately or should we treat them as the same? That's the question. You can see here that suppose we allocate a register R1 to this V2 and R2 to this V1, then the question is this, that what do we do with this V? Because in one case, when the control flow comes from the right-hand side, we should be really looking up V in R1, whereas the control flow, if it comes from the left-hand side, we should be looking up V in R2. And that's not right, because obviously it cannot be both in R1 and R2. And so therefore we must merge it. So we merge these two live ranges like that. And this is what is called as a web. So what exactly is a web? Web is a closure of these different live ranges, provided they share either a definition or a use. So in this case, the use is shared by two live ranges, so we must merge them together, and that's a web. In other cases, transitively, you can extend it here, for example, in this diagram which I have drawn. And these two uses of V, here and here, they share definitions. So we must again merge them, because we can't give again two different registers to them, and we must merge them. And so DU and UD chains closures of those across live ranges is basically a web. And that is what, in this case, we'll have one big web going from this use to this definition, to this use, to that definition, and it will cover all these different uses of this V. And this whole thing will be a web of V. Of course, if there could be multiple webs of V, if they don't share a definition or a use, then they will get split up in different pieces, and we will treat them differently as far as register allocation is concerned. An example of that will be as follows. So here we have, or in fact, even within a given basic block, we have V1 here, and this is our last use of V, and then we have V2 here, and this is our last use of V. So you can see here that they don't share really any definition or use in their live range. If the live range goes to the last use and definition point, so this is our one live range 1. This is our second live range, because it extends from last use again to the definition. And in between there are different uses, and we are told that we should give a register to this guy from here to here in 2 or in 1. And you can see that they don't share really anything in terms of definitions and uses. So this will result in web 1, and this will result in web 2. And we may end up giving register to this guy as R1, and we might give register to the second guy as R2, which is just fine. Or we may not even give, if we don't have register here, we may not even give any register to the second one. We might just give it to 1, or vice versa. So they are totally independent of each other, and they will be treated if they don't share a DU or a UD chain together, the two live ranges and their transitive closure. So we'll separate them into webs like this, and again, we'll build an interference graph of whatever this W1 interferes with. So this will be our W1, and let's say that we have a variable a in this case, which is interfering with it, and we will have, let's say, W2, and we have variable b interfering with it. So this is the kind of interference graph we may have, and maybe a and b also intersect here, and so there may be an edge between them. But we won't have any edge between W1 and W2, because obviously they are totally disjoint, and that's the definition of web. So this is how, so we first find live range from going backwards. I will do that analysis next time. Then we do a DU-UD chain closure of them to generate the web, as in what I showed on the previous slide. And whenever they share DU or UD node, they will get merged, and then we'll build them into the graphs, interference graph. Again, what is interference graph showing is if a web interferes with another one in terms of its live range. So here it will be interfering, W1 interferes with A, W2 interferes with B, W1 and W2 of course don't interfere. They have nothing in common in live range, but A and B might interfere. And so this is the kind of graph of interference graph it will get. So how many registers are needed for this to completely color it? You can easily see we need at least 2 registers. So this is, let's say, red, this is blue, this must be red, and this must be blue. So within 2 registers, we can color all of these, this type of an interference graph. And so how many registers are really needed? How do we most efficiently color them? This in general, an NP-complete problem that we'll solve using heuristic. Obviously, we don't have time to do this NP-complete problems in exponential manner. The compilation time will explode. But we'll see an interesting ways of solving this efficiently, doing some transformations on the IR, again splitting them, etc., which will help us simplify this interference graph and do it efficient in terms of coloring. And so we'll see that, and we'll also look at liveness a little bit. If we had lesser than 32 or 64 registers, then what do we do? Well, our goal will be to pick out of these nodes for which we cannot find a register, the one which has the least spill cost. Basically, what it means is, what is the spill cost of a node? So let's say number of uses that we have of this W1, and there's one definition. So if we don't give a register here, we'll have to put one store here at the definition. And for each one of the uses, we'll have to do a loads. So the total number of loads and the stores that we need to get a value from memory is called as the spill cost. And so out of this graph, if we don't have enough registers, our goal will be to deny register to the node which has the least spill cost. So if one guy has 100 loads and 50 stores, in its live range versus in its web rather, and second guy has only 5 and 5 of stores and loads which it needs, if not in memory. Obviously, this the node which has least spill cost, which is 5 loads and 5 stores, it will be denied a register, and we'll use it for the 100 and 200 100 stores and 200 loads web. So that's how this coloring process will be driven. But there are many parts to this. Who interferes with whom, where this has lots of load stores in that region of interference, whether we can move this around, whether we can split a web, whether we can pull the 2 webs together, and all these kinds of issues will be addressed. And the process itself is heuristic. It is not an exhaustive enumeration because it's has to be finished fast. Otherwise, it's really an exponential algorithm for best determining the best coloring. So, but the heuristics are good enough, and very good solutions through some transformations. So that's the topic for the next lecture. Thank you. Then we'll see you. If anybody has any questions about today's material or in general or projects or whatever, or homework, we have office hours again right now. So see you there. Thank you and bye-bye.